Quality did go in before the name went on. This is a 1970 Zenith model A3720. It's a 16-inch color portable set, and it's worked pretty well. But I had a problem the other night with it where the picture went out. I lost all the high voltage. The sound still works. The tuner works. I can hear snow when it's off channel. And so that means the tuner, the IF, the video detector, the entire sound circuit, that's all fine. The power supply would work because there's bias voltage to run that, but there's no high voltage. So we're going to take this apart and we're going to fix it.
I sounded pretty confident, didn't I, that we're going to take this apart and fix it. We'll do our best. And so follow along with me. We're going to take this cover off together, and I'll tell you a little bit about the set. Have to take off the tuner knobs, and then on the side here we have 3 control knobs: brightness, contrast, and vertical hold. I bought this set a couple of years ago. Turn it. Bought this set a couple of years ago from a collector friend, and it worked at the time when I got it, and he had told me that he had done some work on it. He recapped some of the electrolytics, and the deflection yoke was changed because the original one was disintegrating. Let's see if you can see this better. So there's been work done on it, and it has had some high voltage problems. He had told me that he had this high voltage problem, and he thought he solved the problem with replacing the aging deflection yoke. And I also noticed that high voltage problem. What would happen is when it would run, after a few minutes of being on, it would the high voltage would start to fade away. And if you just left it on long enough, it would fade away to nothing. And I had fooled around with it a lot. I really didn't know what to do. I even replaced the flyback at the time. I didn't think the flyback that was in there was bad, but it had a lot of wax dripping inside. And for the spelunkers watching this, it dripped in the formation of stalactites and stalagmites. So I was able to find a flyback transformer on eBay from a gentleman that had a bunch of them, and it was only $45, and I thought it was a perfectly fine investment because this set is actually really important to me. This is not the exact same TV, but this is the same model that my family had when I was growing up. So I must have been about 9 or 10 when we first got color TV, and this set worked reliably for 5 or 6 years before we ever had anybody have to come out and service it. And I watch a lot of Johnny Quest and a lot of Star Trek on a set just like this. So this set is, to me, kind of cool. So I was really trying to not cut any corners on getting it to work properly. And I finished recapping it, and as I mentioned, I put this new flyback in it. And I also replaced the high voltage rectifier with one of those selenium sticks. So when this stopped working, I was concerned that there might have been an overvoltage, overcurrent situation, because it kind of sat there for a little while before I shut it off. And I'll tell the truth, I was watching an episode of Columbo on this old set. It was the episode where a guy kills another guy, and Columbo has to figure out who did the murder and how they did it. I guess it kind of sounds like all of them. But that was the episode. and I fell asleep watching it. And when I opened my eyes, the sound was still working, but the picture had gone dark. And with my hand, I felt the face, back of my hand, I felt the face of the screen, and there was no high voltage. So it was peculiar that the RF and IF strip and the sound circuit all worked. Somehow, again, somewhere we lost our high voltage. So we're going to start by giving this a visual inspection. What I see right here makes me feel better, because I was concerned that the horizontal output tube and the damper might have been red plating if the oscillator had stopped. I really don't know how long the screen was dark. Let that be a lesson to all of us. It's kind of rule number one in vintage TVs is don't leave it unattended. Technically it wasn't unattended, but you know what I mean. Well, here's the horizontal output tube, and that's the damper. And they look pretty good. I was very concerned that they might have red plated, and if they did, it didn't do that for long. So we're going to pull them out and test them, but I think they're fine. I think they survived. This 6LF6, they've become very expensive tubes. They're used by the audio community now and amateur radio operators. They're just a robust and powerful amplifier tube, and they were designed for TV sweep action, but they're used for other applications now. So they're very sought after. They're probably $50 or $60 to get a good one. So let's pull them out and test them for starters. So the damper is a 6CG3, and on this tester, these are our settings. That line shouldn't be diagonal. The piece of plastic has fallen inside and it's really hard to get to, so we compromise. Type 3, 6 point, so there's our type 3, 6.3 volts. Our plate setting, 18. I found that you kind of have to go up a little bit with it, so I went up 2 points to 20. And we set our levers at D and K going up and GM going down. So D and K go up, and G and M go down. And let's turn on our line voltage. This is where we set the line voltage to the middle. And let's put this baby in here. This is a Compactron tube. Probably saw it flash. And yes, we have glowage right away. And if it was shorted or leaking, we'd see something right away here. And this is our test switch. Let's just see. Yeah, we're in the good and it's going up. So the damper's fine. Damper's fine. All right, we'll put the damper back in. Let's pull the horizontal output tube out. In fact, before we do that, let's set our settings. So let's clear everything here, and let's drive the wheel to, it's a 6LF6. 6LF6. Like Vegas. 6LF6. 6LF6. It's back this way then. How clever. It actually really is very clever. 6LF6, LF6, 6L. 6LF8, 6LF6. 6LF6 type 3, we're there. 6.3 volts, we're there. Plate 18, we're there. CL and DK go up. CL, CL, D, K, and EJ, and then N also, and then the bottom is BM, M. That looks right. Yep. CL, DK, CL, CL, DK, EJ, N, and BM down. All right, let's pull this out. So this is our little horizontal output tube plate cap holder. I had to glue it, it's pretty fragile. Let's see if I can even get it out now without busting something. Okay, 2 hands. It's like this thing really did get hot. And it doesn't fit very snugly anymore. Wow, that's an interesting clue. All right, well, let's test this. Well, see how it's sort of brown on the inside? That's from a lot of use. But oftentimes when it turns brown like that, it looks like it's been swished with coffee. That's because it's been in an overcurrent situation. That's too bad. All right, well, we'll see how it tests. I don't like that. I just saw it open. All right. So, alrighty, we're letting this warm up. Let's make sure we have heater glowage. Yes, we do. So, no shorts and no leakage. And let's test it. Well, it's coming up. It doesn't say it's bad. I mean, so I guess it's all right. It'll produce a picture, provided other things are all right, but probably gonna need a new LF6 LF6 in my life. I didn't buy a spare because they're just so darn expensive, and I really didn't think I would ever need one. Well, you can see the new flyback. This is a new old stock Thordarson. And down here is the stick rectifier that I had replaced the tube rectifier with. Since there was so much wax in the old flyback, I was just trying to get the set to run cooler. And it's bizarre that that plate cap up here, this still has me sort of concerned, baffled. This was an unused flyback when I got it, so whatever we see that looks funny here was from this installation. And I'm not even sure if we can test these. And it doesn't smell. In fact, the chassis doesn't smell now, nor has it ever smelled of anything that's burned. So I don't smell any burned components that might be a telltale, give us a telltale sign. Well, just giving it a little bit more of an inspection. This flyback is in perfect condition. This was an unused wire, and I had just tucked it in here. I don't think that arced. No. All right. Anyway, so this is the flyback. It's beautiful. New old stock flyback. And so I won't believe that this is bad, because I didn't even really believe that the old one was bad. I want to just show you this. This is the box the new one came in. Thordarson. And it replaces all of these other Zenith part numbers. So I think the sheet in here said this flyback was made in the 80s, I think. There's something that's very curious in here I wanted to show you, which is right there on top, but I'll put that off to the side because I wanted to show you the data sheet first. Why? I don't really know, because I thought it might have a date on it. Maybe not. Okay, well, anyway, there's a data sheet in here. Well, this is the old flyback, and I just wanted to show you the stalactites and stalagmites of wax dripping there. It's just odd. I never thought, I didn't know that Zenith used wax as a dielectric in any of their flybacks. I thought it was all a potting material. So I don't think this electrically is bad, but the leaky wax just seemed like, in my quest to try to figure out what the problem was before with the fading high voltage, eliminate the questions. But what I did want to show you is that is this that was in the box from Thordarson. They had, uh-oh, the envelope has sealed itself. Oh, I opened it. Hold on. Yeah, so inside of the box, Thordarson was giving out McDonald's coupons. And the date on it would be the 1984 Olympic Games in LA. So they were giving out, I think, what is it, a whole, they're each 50-cent coupons. So $1.50, $1.50 worth of free McDonald's food, but you had to use these coupons by December 31st of 1985. So when I got this, I wrote to the guy and I said I wanted my money back because the McDonald's coupons were outdated. No, I didn't. I was just kidding. Actually, he and I got a good laugh out of that. These are the power supply caps. And here's the power into the chassis. There's a inductor and some caps across that. And that's because this is a hot chassis set. And I'm sure that, like many manufacturers, the reason you go with a hot chassis design is to try to reduce weight. You don't have a gigantic power transformer. The power transformer that's in here supplies filament voltage for the picture tube, and they float it up with the B+ to reduce the potential inside the CRT for arcing. And here we have the heater voltages for the rest of the set, and you can see the fuses here. I don't think any of the fuses are blown. Another fuse here. And it also provides the 24 volts for the solid state components. So this is the rectifier for the solid state. I guess this is a 24 volt output. There's it's filter cap, it's a Zener diode which regulates it, and output is 24. There's two sources, two 24 volt sources. And some other filtering. But going back to the initial input, that's our line voltage coming in. That's our switch in front. Fuse, thermistor, typical thing for the degaussing coils. But you can see right here, this goes right to chassis. So presumably what we want is the neutral to go to the chassis, and the hot gets switched, but that would depend upon how you plug into the outlet. And I'm going to change this to a polarized plug when we get this all going again. And I wonder if well, we'll look into it, but I wonder if this hot chassis design has something to do with this fading high voltage. I wonder if somehow they're related. But you can see what happens. It comes in and goes right across. These two caps go right across the line
and there's a coil in there for filtration, noise filtration, and then goes right to the chassis. So these hot chassis sets give me the heebie-jeebies in a way, and we must use an isolation transformer before we do anything, before we power it. Must be an isolation transformer in order to work on the set. So we'll get into that at the time. So keep the hot chassis thing in mind.
All right, so our first order of business is this. That is the isolation transformer. That is a must-have. And with that, we are going to use the kilowatt meter. And it's kind of a goofy plug thing I got going on, but it fits in there at the right angle. And I can monitor the current and everything I need to see right there. I'll typically prop one side of it up with a block of wood just so I get a better angle at seeing what is going on. And we're going to check, or we'll monitor, the cathode current. So I have this. I'll show you closer, but this is one of those fairly inexpensive analog meters from one of the big box hardware stores, and it'll read current up to 250 milliamps. So that's become my cathode current meter. And this is a cathode current adapter. It goes between the horizontal output tube and the chassis. And pin 2, which is traditionally the cathode, is interrupted. So by shorting these two, the tube would operate normally. But by separating those two and putting a cathode, putting a current meter between them, an amp meter, milliamp meter, then we get to see what the current is on the cathode. All right, so we're also going to monitor the horizontal waveform, provided there is a horizontal waveform. So we'll clip that in, and we're also going to take a look at, monitor the boost voltage. And we're going to look at the high voltage, because we really don't know what we're going to see when we turn this on. And we probably won't have more than maybe 30 seconds before the current draw in the horizontal output tube exceeds where it should be. I just want to make sure that we've got as much information as we could get all at once. So I'm going to take this high voltage probe and I had done it before, precariously balance the high voltage probe under the cap of the second anode. And the meter itself is right here, so we'll be able to see it clearly. We'll put that up on a block of wood. Well, here's our cathode current adapter. Goes right inside of the socket. I'm just looking at it at a funny angle. Ha! All right, so that's that. And then these two, those are weirdly big alligator cathode current meter right there. So we're on 250 milliamps. So all the way up to the end of the scale is 250 milliamps, and this tube is rated for 200 milliamps. So it's fairly easy to spot. And then once we have our adapter on, we'll just put our... That is our
way of testing the cathode current here. Let's put that like that. Should I put that like that? Let's put that like that. There we go. Yeah, so on that high voltage probe, I have it tucked underneath the cap for the second anode lead. It's in there pretty securely. Otherwise, it's precariously balanced on the convergence assembly. So we've got that, and then over here the meter is going to be in clear view for us. Horizontal output tube, damper tube over here. Have our adapter for current testing, current monitoring. We have our new old stock high voltage rectifier tube in instead of the stick. And we've got our leads from our cathode current checker. Just taped them up a little bit. So not that the two of those grounding would do anything, but it's like if those gigantic alligator clips touched the chassis, that would be bad. So that's what we're gonna do. And then here we're gonna hook this up to find a spot on the schematic for the boost. There's our high voltage. And we gotta find a spot to clip in our scope for the horizontal waveform. And then we got our big guy Syncor scope for the vertical. Let's get that going. All right, so here's the horizontal section. The oscillator and the output tube. And we're looking for where we would find this waveform. And it appears to be on this pin here, pin 5 it looks like. DC voltage, it should be quite negative so that the tube defaults into non-conduction, and it has to get a forward going pulse to conduct. So we'll look for pin 5, and it happens to be right here where I connected the scope probe. That's pin 5 on the horizontal output tube. I've just got a clip to the lead on a resistor at that point, and so we'll see it here. And then we need to find the vertical, and we're looking for this waveform. It's a completely different time base, so we're going to use two different scopes. So we're looking for pin 6 of the vertical output tube, and it should be 0 volts DC. So the vertical is here. This is the vertical output tube, and we said pin 6. And I've got pin 6, there's a green wire, it's hard to see. It's coming out of pin 6. It may look like it's pin 7, but it's actually pin 6. I've got the scope probe clipped onto that. So that'll give us, that'll tell us if we have a waveform or not. And while I was fishing around in here, I noticed this capacitor. Now that is bad. This capacitor is dripping wax, and it's supposed to be a 0.0039 at 10%. It's supposed to be a 10% cap. And I just saw it, and let's look at where this is in the schematic. This is it, 10%. And this vertical circuit, before we go any further, we don't want to dwell on this at this point, but the way of the oscillator and the feedback is such that the signal that comes off of the plate of the vertical output tube goes through this shaping network. Goes through here. And then unfortunately the schematic is cut there, but it loops back into the grid of the oscillator, the multi-vibrator.
and then it goes through the service normal switch in normal position. The output of this plate feeds back into the grid of the output tube, and it's got this self-sustaining action. That's how the oscillator works. And this particular 0.039, I said a 0039, it's a 0.039. I don't know what that does. It's just part of the circuit, and then it drains to ground. So this is suspect. I wouldn't think that the vertical circuit would have enough influence to crush the high voltage, but that's definitely a capacitor we've got to snip out and test and change. And I know I don't have one of that value. That's a 10%er, but absolutely shouldn't have wax dripping off of a capacitor like that, and it's not coming from anything above it. So we'll keep an eye on that. Oh, wait a minute, look at this. Is that the same thing? It is. That's also dripping wax. We'll have to find out where that is. 0.0039 at 10%. So the manufacturer of those two caps, you can see them here, here, and yeah, that is not supposed to look like that. So we'll try our first power up and we'll go from there. So now we need to find a place to monitor our boost voltage, and down here makes the most sense. This is the flyback. So let's just back up a step. So our horizontal output tube is a very high-powered amplifier. And it drives into this winding on the flyback transformer, and it's essentially a auto transformer with a secondary up here that pulls pulses off and goes to different functions: vertical circuit, AGC, blanking. So we're going to look here at the high voltage section. The boost voltage comes off of these windings down here. So it's essentially one tap that splits, and one side of that split goes through a 33K resistor and knocks it down to 850 volts. Otherwise, the boost source is 860. So this is our source. It's got the dots. That's our source. And then these connections here that have arrows that say boost are the points where they connect to that boost source, essentially, in the schematic. So one thing we need to keep an eye on back here is in the vertical circuit. Without boost voltage, the vertical circuit probably wouldn't run. So we'll take a look at that. And in our pin cushion circuit, there are two boost points that drive the pin cushion amp, because there's a lot of juice that has to be driven into the deflection yoke for the pin cushion, because the pin cushion amp will correct some of the lines, the straightness of the lines on the top, bottom, and the sides of the picture. And then there's another boost connection that goes into the plug of the deflection yoke and takes it into boost voltage into the deflection yoke. So on the schematic there are, it lists the boost. So it says here there's 8 boost points in the chassis. And right now we're not going to worry about where the boost voltage goes, but it's just something to keep in our mind. So there's 1 point here for the vertical circuit, 3 points here, 2 for the pin cushion, 1 for the deflection yoke. These 2 points down here go to the, well, back into the high voltage system. So there's a capacitor here, a boost cap that does some filtering, an inductor, capacitor, and inductor. This is the damper tube. And then I believe there would be another boost point or 2 here at the back where the CRT is. So this would be a tap for the focus. So you can tap into boost voltage, B plus, or nothing. for the focus grid, and the boost comes in here and it ties to the 3 screen controls. A lot of juice there. So that's 2 boost points. 3, 4, 5, 6, 7, and then 8 would be the vertical. So those are the boost points we're going to probably have to pay attention to, because, well, let's see what happens when we start it up, and we'll learn a lot then. Right here is the boost cap we looked at on the schematic, and I'm just tapping into one side of it. So that should give us boost. I'm not sure which side of these screen controls is B plus and one side is boost. And then up on top, not exactly sure which one. It's not clearly marked, but this is the focus wire. Black wire is the focus wire coming off the CRT socket, and I think that would be boost, that would be B plus, and one would be ground, chassis ground. So I don't think it's labeled. Oh, it is labeled. Look at that. Oh my goodness. Oh, look at that. Zenith is so clever. There we go. Now we know. So that's how you change the focus. You choose one of those 3 tap settings. So currently there's boost there on that. Okay, great. And this is our service normal switch. We'll put it in run normal position, so that's where the oscillator will work. That's something we'll keep an eye on, whether the setting of the vertical whether the vertical oscillator is running or not, if that affects whatever our situation is going to be. We'll take a look at that. And then we didn't really look for it, but there are fuse wires in here. I'll have to find them, but we're gonna just start off by assuming that because we know that we have B plus, because the sound circuit and the tuner works, and we know that we have 24 volts because the IF strip works, that our power supplies are all in operational condition. I'd have to track down those fused wires. They're little tiny wires in here. That's what they use. And then there are 2 bell fuses up on top, and they appear to be good. There's one back here, and then one right here next to the power transformer. So this does not, this is not B plus. This is filament voltage for the picture tube and everything else, and 24 volts out for the IF, and that's the IF strip. And then there's a handful of transistors in here. I did take a quick look at some of them, and none of them seem to be bad. But this is a high voltage problem. This is not a signal problem. I can be confident in saying that until I'm wrong. All right, we've got things hooked up. Now we need to plug it in. And I'm going to save this going to the chassis last. But we need to plug in our Sencor scope. So our scope on. It's going to be hard to see the scope because we are outside. We're gonna just completely ignore these guys that cut a tree down over here. There we go. It's within their rights to make as much noise as they want, but it certainly is annoying. Anyway, quite a setup what we got going on here. Got the big Sencor scope. We got our high voltage meter, boost meter, cathode current meter, waveform analyzer for the horizontal, isolation transformer must have. We have our horizontal output tube, its adapter. You have a glass high voltage rectifier tube in there. High voltage probe stuck into the anode cap. And now is the moment to plug this in. Too bad this isn't long enough. Let's move this like that. My favorite thing in the whole world are these modern power strips that have these completely inflexible cables that come out. I mean, this is a bigger problem. It's growing more and more. All these manufacturers use these ridiculous cables that don't flex. And it ticks me off. Okay, so, all right, so we should see something on our kilowatt meter. So that's the line voltage, 120 volts, 0 amps, 0 watts. So we're gonna keep it on current, and we'll keep an eye on that. I should have the settings correct for the time base of the vertical circuit. Let's just turn it on and see what happens. The power switch is over here. We're gonna look for overcurrent. First, we're going to look for the current draw. Right off the bat, our set's only drawing an amp. When it's running fully, it draws 2.1 amps, so there's no excessive current at this point. We absolutely have a horizontal waveform. We've got boost voltage coming up. Here comes our cathode current. And as that comes up, we don't have any high voltage at this point. Cathode current. Do we have vertical? We have a vertical waveform, we do. But it's full of noise. Something is grounding. We do have some high voltage now, 15 kilovolts, but that's not enough. Our cathode current is already past 200. Our boost voltage is going down. And here goes our high voltage. All right, let's shut this baby down. It's already, and our current draw is 2.1, so it's more than it should be, but it's not excessive. All right, well, that's what we have here. What did we learn? Well, we learned that this is concerning. We have a lot of noise on the vertical waveform. I mean, I wonder if something's related to this capacitor that we saw, how gross looking it is. But that jitter that noise on the vertical waveform implies to me that there's arcing somewhere. And the boost voltage didn't get very high. 300 volts. And that's certainly not enough to make anything work that needs the boost voltage. And our high voltage only got up to 15 kilovolts. Not nearly enough to make a picture. But we did have a horizontal waveform. Need to put this up somehow so we can see it better than what we had. All right, let me do a couple things here. All right, let's try that one more time. We'll keep an eye on whether or not we can see the filament glow inside of the... But that filament wouldn't start to glow until there's high voltage. So that's the difference with a stick rectifier. So let's look at this right away. Look at this. We have horizontal drive. And we do not have excessive current. We have sound. We can hear snow. You can see our boost voltage is coming up, coming up, coming up. 600. Okay, that's interesting. We have an ugly vertical waveform. And the frequency is not correct. Our high voltage is already fading. Our boost voltage is already fading. Cathode current is too much. chassis current is too much. Darn it. All right. Well, we learned a lot. We just have to figure out what we do with that information. What do we not have? The vertical circuit seems like it's really straining to do something. And those two capacitors we looked at, the one that's really dripping wax right underneath the socket is this one, and that other one is right here. So there's two caps that have similar ugly looking exteriors, which we have to look at. Those are going to be a problem no matter what, but I wouldn't think that that would be enough to prevent the set from building up high voltage, but maybe. In our vertical circuit, there's boost that comes in through this 3.3 meg through the thermistor and into the wiper of the height control. So in order to get the vertical height, there needs to be more voltage than the boost circuit, more voltage than the B plus circuit would provide to get it all going. So we would expect that we'd have to have boost to get a full raster for sure. So the waveform, there was a waveform there. It just was windy day today. So when we switch it into service mode, that disables the vertical oscillator, and the boost voltage got higher than it did with the oscillator engaged. We don't know about the pincushion amp. Although I'll tell you, off camera, I pulled the tube, the 6AH9, and turned it on, and it didn't make any difference. So I don't think this is a problem in the pincushion amp. I doubt very much it's in the deflection yoke. So let's look at our horizontal. Let's talk about how this even happens. So that's the yeah, okay, so that's the automatic frequency control. So horizontal oscillator feeds the horizontal output tube. We should look at this DC voltage if it's a negative. In fact, let's do that right now. All right, we're just starting up. Here are snow, here's some boost. So I use this scope for the horizontal, so we have a nice horizontal waveform. I really wanted to see what this DC voltage is. So there's a negative 57 volts on that grid. All right, and I'm gonna kill this because we've already got a runaway cathode current. All right, so you can see that we don't have a lot of time. And then this is another problem, the scope. I know what's wrong with it. It's a lot of work to take it all apart and fix it, but the horizontal waveform on this scope, which is a great scope, it collapses all the time. And it only does it at the moment when you really need it. So this is another repair video. So that was where we were just looking. We were looking for that voltage. It's a minus 57 volts, so it's negative anyway. That's good. And I wonder what might affect it in terms of a control setting. Maybe once we get this working properly, we'll adjust the high voltage to what it should be, and we'll see how everything falls into place. So in order for the boost voltage to work, the horizontal circuit has to run correctly. And in general, it's a pretty robust, it's amazingly robust, these circuits.
for what they do. So the oscillator, making its circuitous path through here, well, not into here, but into here, the oscillator creates its waveform, gets its waveform from these filtering networks, and it puts a drive on the grid of the horizontal output tube. From the horizontal output tube, it goes into this winding on the flyback transformer, and it gets boosted, stepped up to create the boost source. So there's 850 volts roughly. This is 850, this is 860. There's just a dropping resistor right there for two different taps. So we have to have the horizontal circuit running in order for boost to get manufactured. And this goes to the picture tube. That's the high voltage, the second anode lead that goes to the picture tube. This has to be upwards of 21,500 volts, and this is our rectifier tube. So in order for the rectifier tube to start conducting, there has to be voltage across the filament, and the filament gets its voltage from a 2-wrap winding off of the secondary of the flyback transformer. So the high voltage has to work in order for this to conduct, because it gets its filament voltage from the flyback. So there's a lot of things that have to happen in order for this to work at all, the set to work at all. That's why it's so amazing. It's kind of the black magic section, because it's really pretty amazing that these work as well as they do, these high voltage circuits. So we have our damper. Our damper works in unison with the horizontal output tube. The damper actually controls half of the scan on the horizontal sweep. Part of it is energy from the damper, and part of it is energy from the horizontal output tube. And there's a period in there where they're coasting. It hands off the scan from one to the next. Again, pretty amazing. So something's loading this down, and the problem is that you can't take things out to eliminate them from the circuit, because everything has to be working in concert to work. So this particular situation where you've got a high voltage problem, it might become just a hit and miss thing. Off camera, I did disconnect a few things. I took the high voltage lead off of the picture tube. That didn't make a difference, and that tells me that the picture tube is fine. I suppose a heater cathode short back here, no. It would have to be something pretty bizarre happening in the picture tube to be the cause of this load. And it was working fine. And you know, the picture tube and the vertical output transformer, those are the two pretty much unobtainable parts. I don't think I'd ever be able to find one of those picture tubes. This is a goofy one. It's a 15 AC P22, kind of an odd size. And then the vertical output transformer, that does a lot of things. The pulses from the vertical circuit come off another winding or two, and then they go into the convergence circuit. Convergence circuit and the deflection yoke. Deflection yoke is here. This is the dynamic convergence circuit. So on some of the older console TVs, when this vertical output transformer was prone to short from the primary into the secondary windings for the convergence circuit, then you've got a mess, but you still had sweep, horizontal sweep, and high voltage. And I know on this particular set, if I unplug this convergence socket plug, unplug the convergence panel, when it's working right, you have a raster, but it's all broken up. So you have to have these two
hooked up for it to work properly. In an older console set, you could pull that convergence circuit out of the chassis, and it would work just fine, minus the dynamic convergence.
Well, there's the problem. Right there. No, I'm kidding. Other people have said this about Zenith chassis, but there is something that is just mesmerizing about this hand-wired chassis. The color sets have so much complexity to them, and the possibility that a manufacturer could keep all this stuff straight, and you can kind of get an idea when you look at these in detail that they built them up in layers, so you can see the components that were probably put in first, and then the next ones and the next ones, because things get buried. So going back to some of the things we were looking at, let me even add a light here. But there's another thing that I noticed that I'm not sure what to make of this. There's this capacitor in the center of the frame, if I can hold the camera steady. This is the damper tube socket, and next to it is the horizontal output tube socket. But the damper tube has, right across the damper is a capacitor. And that's done for who knows what, but I had read an article and I was trying to get the cathode current before, when I had this reoccurring high voltage problem. I was trying to do what I could to reduce the load on the high voltage system. And I read an article or a thread from one of the forums about changing this capacitor across the damper, and that as you go up in value, you should go down in cathode current, and it's a slight amount, but as you go up in value, you go down in cathode current, but you do get a wider picture, which you may not want. And this particular set does not have any kind of a horizontal size control in it, so you get what you get. But I was just looking at this, and it struck me that that component I put in because I was trying to reduce the cathode current. But this is another one that I had at the time, identical to it. And just because this is badly discolored doesn't mean that it's bad. I can't test this inside of the circuit because on either side of it are these two inductors that go to ground. So we got to lift this out and test it. But holy mackerel, this is discolored, and you know, I really don't use this set, hadn't used this set that much. So this kind of surprises me, what we're seeing here. This is a 100 picofarad cap. I just tested it. The one I have in my right hand that I'm moving is a 100 picofarad cap, but it at 6,000 volts. It tests higher. Should be 90 picofarads. I think I was looking to put 100 picofarad in there. So I was just fooling around at the time. Kind of forgot about this. And this was the original one that was in there. It's a 5,000 volt cap, and that should be a 90 picofarad. I just tested it, and it's 117 picofarads, so this has gone up in value too. I have something that we could put in there. So I'm going to get out the soldering iron, and I'm going to pull this out, both sides, and we'll test it, and we'll swap it, and we'll give it a try. And these other things we're going to hold off for a minute. There isn't much room. They're really jammed down in there. So we talked about how things were probably built in layers. This particular cap may have been put in there early on. So the best we can hope for is probably to snip the lead with enough room on the end to make a hook and tack in something new. There and there. So, okay, well, we're gonna start up here. This is the damper, right across the damper. Okay, so just as a look-see though, this is what it is. This is that capacitor we were just looking at. And it's right across, literally across the damper. That could be something. We'll check these inductors. But you can see there's a lot of action that goes on here. Comes right off the boost cap. Yeah, maybe. Let's take a look. Well, either the component was super brittle or I mangled it up just trying to get it out. I think the second one. This is the same capacitor. It's hard to read. But I can see that it's a 100 picofarads, so went from here to that in a short period of time. Anyway, this is the moment of truth. It doesn't mean that it's bad. Let's see what this is. Testing! Oh, what? It doesn't even know what it is. It's no longer in anything. This might be the ugliest solder job ever. I'm sorry you couldn't see that. All right, well, I think I've got this hooked back up again to a point where we can try it. Sometimes you just get a sense of dread because it was just too easy to find it. Let's turn it on. Let's see what happens. Just finding that part seemed too easy. So look at our boost voltage. Look at our chassis current down here. Boost voltage is going the wrong way. Cathode current is coming up, but currently no high voltage yet. Maybe because the rectifier tube. Whoa, I heard high voltage! Uh-oh, there's arcing in there. Okay, so we have something positive happening. I just don't know what is going on there. Shoot. I uprighted the chassis. I took the high voltage probe out, at least for now. Just wanted to flick it on and see what we see. And I'm not sure what to expect. It sounded like for a moment this vertical was running, but it didn't sound like it lasted. Boost voltage didn't come up, but the cathode current was hovering. So right there is about 200 milliamps right there. So that seemed all right. I don't expect to have a picture because I don't think we have enough. Well, we'll see if we have horizontal sweep because we won't have boost voltage until we get horizontal sweep. And until we get horizontal sweep, we won't have filament voltage for the high voltage rectifier, which means we won't have high voltage. So we're going to just see what happens here. Power on. An amp. So this is looking all right. The current draw seems about right. An amp, 1.2 amps. Okay, we have sound. Our cathode current It's coming up slowly. Our boost voltage is going to 400, 500. All right. Oh, I see filament glowage inside. Oh my goodness. Do we have a picture? Do we have a picture? We do not have a picture. Oh, we do. We have a raster. Holy smokes. We have a raster. Wow. Where's our boost at? 800 volts. Cathode current. Where it should be. What? This whole thing is working. Oh my goodness. Let's turn it off. Let's quit while we're ahead. Holy mackerel. Holy mackerel. That little cap dragged this whole thing down. What I did on the boost voltage is I moved the focus lead from the boost pin over to the bias. And I used the boost pin as the point to measure the boost. So I don't know, I didn't pay enough attention to it if it was in focus, but I suspect it might be a soft picture. All right, so we're gonna spark it up again. Let's take a little quick look at it. High voltage probe is precariously tucked up underneath the, I feel pretty confident that that's correct. So let's turn this on. What do we see from here? Our boost is coming up slowly. We have filament glowage. The boost is at 300. We have our sound, so we have B plus and 24 volts. We have our cathode current coming up. No high voltage quite yet. I wouldn't think it's, there we go. High voltage is coming up. High voltage is at 20,000. Cathode current is holding steady where it should be. Well, we have our high voltage at 20,000 volts. Cathode current is good. Let's see if we have a raster. Holy moly, we sure do. We sure do. It's very dim. Let's turn it up. Can't tell if it's out of focus or not. I should get a signal on here. All right, I'm gonna back down. I did look at our chassis. Current is right where it should be, 2 amps. 2.1 is where it nominally runs. And our cathode current is right where it should be, literally. And here we go with our high voltage. That seems a little bit low. And the adjustment is, where is the adjustment? The adjustment is right there, so maybe we'll take a look at that. But let me shut this off and get some tools. This is pretty darn encouraging.